This video is going to take us through hard wedges, wedge factors, and wedge profiles, and I'm going to use the treatment planning system to illustrate this. On the screen, I have set up a 40 by 40 by 40 water phantom, which is kind of this light gray color, and then I have a series of red lines. The vertical red line here is going to be the central axis. It's going to help us determine the percent depth dose, and then I have these three horizontal lines, one going through 5 centimeter depth, one going through 10 centimeter depth, one going through 20 centimeter depth, and they're going to help us visualize the field profiles both for open and wedge fields in this example. So I can compare wedge factors in this video. I have prescribed 100 centigrade times 1 fraction for a total dose of 100 centigrade, and everything is normalized to a reference point at 10 centimeter depth. All of my field sizes are a 15 by 15 field size. I do have one 40 by 40 field size in here to show you how the field profile changes over the entire width of the field. I have calculated an open field with 4 of the hard wedges, 15 wedge, 30 wedge, 45 wedge, and 60 wedge for both 6x and 18x to show you the difference in energy. I want to first start, well, I should go back and clarify. On the left-hand side, I have a series of isodose lines going from 250 centigrade down to 20 centigrade. They won't always all be displayed at the same time, but I've put this many isodose lines on in 10 centigrade increments so you can see the effect of dose on the volume once we start inserting these pieces of metal into the beam. Again, remember that's what hard wedges are. They're a wedge of metal, steel, lead, or a combination of it that's inserted into the treatment head that physically attenuates and modifies the beam profile. So here I have a 6x open field, and I've normalized to 10 centimeter depth, so you can see my monitor units are 142 mu. So 142 mu, that makes sense. I'm 10 centimeter deep. I have a 6x open field. So I'm beyond D max. My percent depth dose is probably something in the 66% range. Plus I have a 15 field size, so we have a change in S sub C and S sub P. Anyway, so the mu makes sense. Now, if I pull in my percent depth dose, okay, this line makes sense. We went over normalization and how normalization changes the absolute value of the y-axis, but the generalized physical shape of the percent depth dose doesn't change. Here I have a profile for an open field size at 5 centimeter deep. Again, we went over this. We have a slight increase in intensity in the shoulder region. These are horns caused by the flattening filter. As we move deeper into the patient, I shouldn't say patient, into this phantom, the shoulder region becomes predominantly more rounded because of the preferential beam energy difference between the lateral portion and the central portion caused by the flattening filter. As I change energy, the general field shape, it remains similar for open fields. It changes a little bit because the 18x profile has a different flattening filter and then different photon characteristics associated with that flattening filter. But the general shape of the open field profile is similar between open field beams of different energies. Now, when I go to a wedge and I insert a wedge into a field, and I am going to put a 15-degree wedge, so I'll turn this field on. So here is the display. Let me turn this little bolus thing off. Okay. So here's the graphical display of the wedge and what's happening. So you can see I've inserted this wedge into the field. I have the toe on this side, the patient's right-hand side, the screen left-hand side, and I have the heel on the patient's left-hand side. Okay, the central axis in the center of the wedge. The resulting isodose distribution, I still have a 100 centigrade line, is normalized to 10 centimeter deep, so my monitor units are calculated to give me 100 centigrade at 10 centimeter deep, so everything above that is going to be hotter. And we see what happened is two things. A, my isodose lines tipped a little bit. Let me go back to 6x open field. And the absolute value of those isodose lines increased slightly. So in the upper right hand corner of the screen, my 3D max dose with the wedge is 160. and my 3D max dose with the open field is 150. So my 3D max dose has increased slightly. That's because of the preferential attenuation, the central axis, and then I have transmission through the toe of the wedge. So what's happening is that the material, the metal in the wedge, is absorbing the radiation, and in order to normalize and get 100% of the dose at 10 centimeter deep, my monitor units went up to 198. So they were 142. So I've increased to 198. So I've had to deliver 50 extra monitor units to compensate for the attenuation of the metal wedge. By doing that, because of the wedge profile, the physical wedge shape, I've preferentially let through more photons through the toe than through the heel. So I'm cooler on the heel side and I'm hotter on the toe side. And this effect gets worse as I increase my wedge angle. So to show you 30 wedge, watch what happens. So the isodos lines tip slightly more, and I get slightly hotter underneath the toe. 45 wedge, the isodos lines tip even more, and I get even hotter under the toe because my wedge transmission is going down on the central axis. I'm having to pump more monitor units in. Now I'm up to 287. I'm preferentially thinner here, preferentially thicker here, so I'm getting more dose underneath the toe. And then finally, if I put a 60 wedge in, you can see what happens. I'm still normalized to deliver 100 centigrade at 10 centimeters deep on the central axis, but now I'm letting through 250 centigrade in the toe side of the wedge because of the transmission. I'm going to go back to 15 wedge, and I want to talk about beam profiles. So here is a beam profile at 5 centimeters deep for 15 wedge. I'm going to go back to an open field so you can see what happens. So I go from a relatively flat and symmetric beam in open field. Here I have a 15 wedge. Here I have a 30 wedge, 45 wedge, and a 60-degree wedge. You can see the relative intensity difference between central axis and the toe, and you can even see it's more pronounced between toe and heel because of the attenuation or the transmission. Let me go back to 15. Sorry, that was open. So this is 15 wedge, 5 centimeters deep. This profile is 15 wedge, 10 centimeters deep. And this profile is 15 wedge, 20 centimeters deep. Okay. Now, I'm going to change here and go between wedges. So first of all, let's go back to open field. So again, 5 centimeter deep profile, 10 centimeter deep profile, 20 centimeter deep profile. Let's go to the 15 wedge. You can see what happens. I get a nice sharp shoulder on the 5 centimeter, but if you go down to 20 centimeter, you can see how I'm getting rounded because scatter's filling in. Scatter is making the beam more uniform at depth because we get side scatter that compensates against the tilt of the isodos lines caused by the wedge. Let me put a 30 profile on. Okay, you can see that. Notice on the 10 centimeter deep, I'm normalized on the central axis to 100 centigrade. That's how I've normalized the plan. Everything else is going to be dependent on the percent depth dose curve as well. 45 wedge and a 60 wedge. Go back to 45, 30, 15, and open. Great, so that's wedge profiles. So monitor units, which are directly impacted by the wedge factor, wedge transmission factor. So we have open field, my monitor units are 142.2. My 15 wedge, because of the attenuation of the wedge, in order to deliver 100 centigrade, I have to increase to 198. For a 30 centimeter wedge, it moves up to 254. 45, I'm at 287. In 60 wedge, I'm at 344.5. So if you want to calculate a wedge factor, you take the dose at depth with a wedge divided by the dose at depth without a wedge. Well, we're normalizing our doses. Right? So I'm forcing the computer to give me 100 centigrade at depth. So instead, we can take a ratio of the monitor units. So to figure out a 60-degree wedge factor, I'd open up my open field is going to be 142.2 divided by, and then let me weight my 60 wedge. It's 344.5, and I get 0.413. Okay, so 0.413 is my wedge factor. How do I know that? Well, if 0.413 is my wedge factor, I can take my original open field monitor units, which is without the wedge, okay, and I would take 142.2 and I'd divide that by whatever my wedge factor was, and then I get 344.5. So that's another way we can figure out wedge factor from the treatment planning system, as opposed to on the machine where we're delivering monitor units to an ion chamber. So how we would do it on the machine as part of your attenuation project is I would take 100 monitor units from the wedge field, see what dose I get, or see what response I get from the electrometer in chamber, and then I'd take 100 monitor units from an open field and then take the ratio of that, and that'll give me a wedge factor. The percent depth dose isn't going to change a whole lot. It is going to be higher at depth because of beam hardening. So the wedges attenuate the lower energy photons coming out of the machine preferentially, so the percent depth dose increases, similar to how the PDD increases when we use 18x instead of 6x. The effect is there, and it does happen with hard wedges, but a lot of people ignore that effect with hand calcs, especially manual hand calcs with like pencil and paper. If you have a third-party software like RadCalc or MUcheck, something like that, you have the option of inputting those wedge-dependent percent depth doses in. So as the lecture notes, as well as Con will tell you, how do we get the wedge names? The wedge names are not given or not described by the physical angle of the metal on the wedges that you put into the machine. If those wedges were actually at those physical angles, they would never fit in the treatment head of the machine. Or if they did fit, they'd be so large, especially the 60-degree wedge, that the therapist wouldn't be able to lift them. So if I weight a 6x15 wedge, and if I take my angle measurement tool, and this isn't going to be perfect, but at least it'll help illustrate. What we're looking at is how much do the isodose lines tilt by. So for 15 wedge, my isodose lines tilted about 17 degrees. So a vendor is going to specify a specific wedge angle based on the tilt of the isodose lines along the central axis at a specific depth. If I take a 30 wedge, and I do a similar thing, okay, 29 degrees. If I do a 45 degree wedge, use an angle tool, I apologize for the delay, 44.3 degrees. And finally, for the 60 wedge, 60 degrees. So that's what the wedge angle is describing, is the tilt of the isodose lines along the central axis when compared with the open field. So in this video we reviewed open field depth dose and profiles. We reviewed what a wedge factor was, how it affected the monitor units being delivered to the machine. We discussed the wedge profiles with depth and talked about how the isodose lines shift within your patient.